not as many people as last time, but it's okay.
Yeah. Okay, cool. We're live.
Okay. Do you mind if I do the introduction, Ayush?
Yeah, no worries.
Okay, awesome. So welcome everybody back again for day 2. We are obviously at the Sea Wonder live learning at home, and we're so happy that everybody could come out. Today, we're going to be talking about green computing and designing for the environment. If you don't know what that means, it's okay. We're really excited to introduce it to you guys. Ayush, would you like to do your little introduction? Next slide.
Yep. So as you can see on the screen, this is my slide. So my name is Ayush Bajaj, and I'm an engineer outreach program instructor, as you guys already should know. And right now I'm in my 4th year, and I'm doing mechatronics engineering, which is pretty cool. It's like a combination of all the other engineerings. So if you have any questions about engineering or just university related stuff, feel free to reach out.
And there I am in my Christmas hat again. I'm Nathan, if you remember me from last time, engineering program instructor, engineering outreach program instructor. I don't teach engineering, definitely not. I haven't even graduated yet, but I'm in my 3rd year of software engineering. If you remember from last time, if not, that's totally cool. And yeah, I'm really happy to be here. We can get into it. So if you remember our code of conduct from last time, joining with your first and last name, microphones and cameras on mute. If you want to answer a question with your microphone, totally fine. Just there's a hand raise button you can use, or just type it in the chat. And speaking about the chat, keep it relevant, keep it on topic. Otherwise, you're totally cool. And respecting everyone in the virtual classroom. Next up is our quick little disclaimer that our sessions are being recorded and live streamed, and the focus is on us, Ayush and I. So just in case, there's no need to turn on your camera or audio, but if you do, it'll mostly be focused on us. And consent to film was completed during the registration process. We'll get back into our little recaps of last time. Remember STEM. This is what we kind of use to try to understand the world. We use science, technology, engineering, and math, and we mix and match between all these fields to solve problems and whatnot. And because we are engineering outreach, we focus on a little bit of engineering. Next slide. And we kind of ask, what is engineering? If you remember what engineering is, it's all about problem solving and using the skills that we learn throughout school and throughout practical experience to invent, design, test, build, analyze, and blah, blah, blah. The types of engineering on the next slide. If you remember these, we have some of the big ones like mechanical, electrical, and maybe like civil. But maybe today what we'll be delving a little bit into is kind of like my field and some of Ayush's field, because he's studying mechatronics, and a little bit of computer engineering. And we are talking about designing for the environment using computers. And let's recap the engineering design process on the next slide so that we know how to solve these problems. First off, we identify the problem. And then after we do that, we're going to brainstorm some ideas. After we brainstorm ideas, we are going to design a solution, and then we'll make a model. After we make our model, we're going to test and evaluate. And once we've hit that sort of test and evaluate point, we can say, okay, did I make an appropriate model? Was my solution okay? If yes, right, you're okay. If not, totally fine. Go back, redesign. Okay. A recap of sustainability. We looked at this last time we got together. So sustainability is kind of like the process or actions through which humans avoid the depletion of natural resources to keep an ecological balance that doesn't allow quality of life of modern societies to decrease. We'll sum it up in 3 pillars. We want to kind of protect society, the environment, and the economy, right? People, planet, profits, okay? And designing for the environment, we can kind of look at that life cycle analysis we did last class, and try to make sure that we are keeping all of these sort of pillars in mind when we design and when we create things. going into some topics for today, we're talking about green computing. And there's this sort of myth about computers where they are paperless, so they are better, right? And compared to sending a letter by hand, yes, they are definitely better. You don't have to put it on a truck and then send that truck to the post office. Then from the post office, it gets on another truck and goes to somebody's house, and then a mailman picks it up, or a mailman takes it from that center and walks it across. When you send an email, it's really quick and whatnot. But there are still some drawbacks to using computers, and we can sort of design them even more efficient than they were before, right? And kind of keep that sort of flow going on where we design better and better and better. Green computing is about being environmentally responsible and eco-friendly, right? In our use of computers, computing technology, and their resources. So there are a couple initiatives in green computing. We want to try to minimize electricity consumption. We want to make sure that our computer design and coding is as efficient as possible. And one of the big ones is proper technological disposal, right? So whenever we finish with our cell phone or whatnot, right, maybe refurbishing it, being conscious where you throw it out, and whatnot. Move on to the next. So there's a little bit of this story about green computing, about a Dutch programmer named Danny van Kooten, awesome person who decided to reduce his carbon footprint by no longer eating beef or flying. And those are really big changes that people can make to minimize their carbon footprint. But Danny van Kooten, being a programmer, made this popular WordPress plugin called MailChimp. I think MailChimp, yeah, MailChimp. And it allowed users to sign up for MailChimp directly via a form embedded in your site. But it made your code much longer. And then a bunch of people were using it. And even times where it wasn't needed, people would be using it, or when it was inefficient. And every time somebody would go to a website that would use MailChimp, all those lines would be sent to their computer. It would take extra processing power, right? Extra server sort of data usage, and in turn, more energy, right? And the more energy you use, right, the less energy efficient you are, right? So it was just kind of burning resources for potentially no reason. Although it was a very, very good WordPress plugin. A little fact about email: if every adult in the UK sent one less thank you email per day, it would cut 16 tons of carbon each year, right? So just trying to sort of materialize this sort of like digital energy usage, right? 16 tons of carbon is a lot, right? So if everybody in the UK sent one less email, and that's just in the UK, it would cut 16 tons of carbon each year. So sustainable software design is ensuring that the design, implementation, and operation of applications have little to no impact on the environment, right? So maybe think twice before sending that thank you email. The next slide, we talk about artificial intelligence. If you know what artificial intelligence is, that's great. But essentially, boiling it down, it's about leveraging computers and machines to sort of mimic the human sort of problem solving and decision-making capabilities. There was this really cool use of artificial intelligence in green computing by Google at one of their data centers, I think at their main data center, where they cut their cooling bill by 40% by only running it the cooling when they needed to, I think, is how it used. I might be remembering the story a little bit wrong. But that graph on the left there is showing what happened when they had their machine learning control on and machine learning control off, and their power usage, right? So that sort of large drop in their power usage was when they turned on their machine learning algorithm to control the cooling of their data center. And then when they turned it back on, you can see it skyrocketed again. So really awesome way to sort of leverage this this new thing that we talk about in artificial intelligence. And I will hand it over to Ayush.
Okay, cool. So today we're going to learn about coding. So has anyone heard of what coding is? Do you know what coding is? Rather than the fact that you have on the screen. Like, do you know what coding is? Can you put it in the chat? just a one line or a one word, that works as well. And if you don't know, that's fine as well. So what is coding? So I'll wait 30 more seconds. So if someone knows what coding is, go ahead and make sure you're the first one in the chat.
And some of us may have some experience in coding. May see some familiar names from our Python sessions. So if you remember
Yeah.
what coding is, that'd be awesome. Just like a quick description.
Yeah.
The chat isn't recorded, by the way. Just to let you know.
Chat isn't recorded. It's just our faces on the live stream. Is a way of giving instructions to a computer, programming our devices to do something. Exactly. So that is what coding is, right? It is just a step-by-step set of instructions that tell a computer or device what to do. It's just like following a recipe. Now, when we follow a recipe, we follow a recipe to make a cupcake. Or an analogy to this is our computer follows some code to perform tasks that we want it to perform, right? So that is what coding is. And now let's move on to learning about algorithms. Has anyone heard of algorithms before? Maybe you've seen someone use that word before, but you didn't know what that means. Just quick yes or no. Algorithms. Have you heard it before or no? Pretty cool word in my opinion, but okay. So we have one yes. Cool. So it looks like we already know what algorithms are. But for those of you who do not know what they are, so algorithms are a well-defined set of instructions for a computer program to solve any specific problems or perform a computation. Now, as you know, if we're performing a computation, we would require resources, which takes time and storage to run. So we define a term such as an algorithm complexity, which represents the amount of resources the algorithm needs, which in turn increases the power consumption. So you can imagine if our algorithm complexity is higher, then our computing resources, which means the data that we are storing or the time and the storage that our algorithm takes to run is higher, which in turn means our power consumption is very high, right? Now, an example of algorithms is Google Maps. This algorithm finds the shortest path from one point to another. Maybe you've used Google Maps before and you know that it's pretty fast. It quickly finds the best possible path from one point to another, right? And more examples of some algorithms are Instagram, Facebook, and TikTok. They use algorithms to figure out what you like to watch, and then they actually recommend it to you, so you actually spend more time on the platform. So you can see that these algorithms are a pretty big part of computers, and making sure that our algorithm complexity is not very high because we need to save our power, right? So making sure our algorithms are not as complex as we want them to. Cool. So now let's move on to some sorting algorithms. So sorting algorithm is just an algorithm that puts elements or objects in a list or a set in a certain order, which is a chronological order. So some examples of this are programming TV to sort channels on base of your viewing time, right? And also we have quickly organizing sports scores in real time. So you can imagine if you have a lot of different sports scores and you want to sort them, you could use these algorithms to sort those scores and then show it on the screen, right? And also we have databases with large amounts of information, which actually need to be sorted because if we have a large amount of information, we don't know where each thing is. So when we sort it, we actually know where everything is, right? So the sorting algorithms are very useful. As we talked about before, we need the complexity to be very low. And we are going to be exploring some of these algorithms today. Okay, so the first algorithm that we're going to explore is bubble sort. So what we do in this algorithm is we actually go through the set or list again and again, and we sort the values or objects that are in the wrong order. Now, on the right, as you can see, we have a GIF, and We'll wait for it to finish and then we will start again. So yeah, so we actually checked 2 and 4, and then 4 and 1. Those were in the wrong order, so we actually swapped them. And then we do the same with 5 and 3. And what we are essentially doing after each run is putting the largest element at the end. And now, as you can see, we put the second largest element at the end. Now we do this again, and as you can see, we get a sorted array. So we swap if they are in the wrong order, and we keep doing this again and again until we get the sorted array. And this is a very basic version of a sorting algorithm, which is bubble sort. So now we will move on to selection sort. Now, what are we doing in this algorithm? So in this algorithm, we actually find the object with the smallest amount and set it aside. So as you can see on the GIF on the right, we actually find the smallest number, which is 1, and we put it on the left. And then we go ahead and find the second smallest, which is 2, we put it at the start. And we keep doing the same process again and again until we actually have our list sorted, right? So you can see this is also a type of algorithm that you can use to sort any list of numbers or a set. So whatever you have, you can use these algorithms to actually sort everything that you have. And make sure to repeat the process. So finding the smallest from the remainder of the list. So first you find the smallest number, you put it at the start, and then make sure you repeat the process again and again until you have the sorted array. Okay, so now let's move on to a little more complex sorting algorithm, which is named quicksort. Now in this algorithm, what we actually do is we choose one object at random and compare the remaining objects in our list with it. Now, how do we do this? So as you can see on the right, we choose a random object, which is 13, and then we compare all the other objects. So if the object on the left is smaller, then we just keep it there. If it's bigger, then we actually swap them. So as you can see here, we swap 13 with 23 because we need everything on the left of 13 to be smaller and everything on the right to be bigger, right? So as you can see here, we check 23 and 11 and we swap them because 11 is less than 13. And then we swap 13 and 23 because 23 is larger than 13. And once we have this, we will also have on the left, we will have a lower value set, and on the right, we will actually have a higher value list, right? Which we will see right now in just a second. So we will so as you can see on the left, we have a smaller, and on the right, we had a larger, right? 51 and 23. Now what you need to do is, after you do this once, you have to make sure that you keep doing this again and again for the smaller one and also the larger one as well. So you know how you are sorting your things. So you basically just repeat the procedure above, right? And remember to do it for the other groups, the smaller one and the larger one. So you take a random object, you compare it, and anything that is smaller, we put it on the left. Anything that is bigger, we put it on the right. And then we do the same thing for the small and the bigger list. Cool. So now we move on to another sorting algorithm, which is insert sort. In this algorithm, what we essentially do is we remove each object from an unsorted list, as you can see on the right. So we remove 3, and we actually go ahead and place it in the right order of the sorted array, which is from 5 and 6. Now we take 1, and we know that 1 goes before 3, so we place it under 1. And then now we actually take our example, which is 8, and we know that 8 has to go right there, but 7 has to go on the left of 8. So we actually take it out and then put it before 8. And then we take 2, we make our comparisons. So we make sure that it is going on the right place. So we keep doing that. And once we find the position, we actually go ahead and put it in. And then lastly, we do the same thing for our last element. Now, as you know already, all these algorithms, you need to keep repeating them again and again. So there you go. So once we complete our algorithm, we will have a sorted list, right? So we select the element, take it out, and place it in the right order as where it needs to go. Cool. So now we have a different kind of algorithm, which is merge sort. In this algorithm, what we do is we divide the set or the list of numbers into two different sets of equal size, right? So in this case, we'll wait for it to finish. And then, so on the left, we had 2, 11, and 23. On the right, we had 13 and 51. So we divide the set into two random sets of equal size. And then we actually sort each of the smaller sets. So we sort the one on the left and on the right. Now, as we know, in our case, it's already sorted. So 2, 11, and 23 is sorted, and 13 and 51 is sorted. So then what we go ahead and do is actually go ahead and merge those two in order of where the elements should go. So we place 2, and then we check 11, and then we take 13 because it has to come after 11, and then we keep doing the same thing until we get to our final sorted list. Now, we know that sorting by merging is actually easier, as you can easily compare these objects one by one, right? So you just go ahead and sort each of the smaller sets and then just merge those sets together. And this is a pretty good algorithm in terms of sorting. So make sure you write that down. Cool. So now let's see algorithm efficiency. So here we have a GIF of all our algorithms running at the same time. So they start at the same time. However, we can see which ones finish first. So as you can see here, our heap and merge sort are already finished, while the bubble sort and the selection sort are still taking a lot of time. Now, can anyone tell me which algorithm has a higher complexity? Is it the bubble sort or is it the merge sort? So if we go back to algorithm complexity, if our algorithm takes more time, the complexity is higher. So which one do you think the complexity is higher in? Is it the bubble sort or the merge sort? Bubble sort, exactly, because it is taking more time. And as we explored before, if our algorithm takes more time, we need more power to actually run our algorithm, right? So we make sure that we choose an algorithm which is pretty lower in algorithmic complexity. So now we have a question where how is this related to sustainability, right? So how is this related to sustainability? Now we already explored this. So if our algorithm takes more time, then what happens is we consume less power because it's not running for that much time. And then we also have another question is, what would the global impact be if every computer code ran 1% more efficiently, right? So you can imagine if everyone in the world right now is using bubble sort, and then we go ahead and add merge sort to every computer that we have, what will the effect be, right? We will all end up using less power than what we are using today, which is really good, right? So we have to take into consideration like the power usage and all those sustainability pillars that Nathan talked about. And also now at the end, I will leave you with a question is, how can you apply this concept to your life? Okay, cool. So now let's start our problem. So now I will turn it over to Nathan, who will talk about our problem.
Thanks, Ayush. Okay, so today, what we are going to be trying to do is designing a sorting algorithm that will best sort a set of electronic waste by weight. Okay, so maybe you have a scale with you, or maybe you can just kind of feel with which one's going to have more weight. But let's first brainstorm some ideas. Okay, so let's go to the next slide really quick. So let's think back to some of the sorting algorithms that we had introduced to us by Ayush. And what are the sort of principles behind each algorithm? Could you possibly create your own? Or which algorithms seem the most interesting to pursue? And why are they interesting? Okay, so let's think quickly. If we wanted to create our own algorithm, what could we do? Right. So I'm not going to try to copy any of the ones we saw before, but I'm going to try and say, okay, so what I'll do is I will take my randomized set of elements, right? So I have these kind of cups in front of me with some water in them, and then I have my digital scale that will tell me the weight. Or I can just pick them up and feel, okay, this one is definitely, if I filled them up, I would say, okay, yeah, this one feels like the one I lifted up the first time, and it was the lightest, second lightest, third lightest, fourth lightest, fifth lightest, and this is the heaviest cup, right? I could do something like that. So let's try to create an algorithm for this. So if I want to do something really simple, what I'll do is I'll lift up every single cup in front of me, and then, or in this case, because I have a digital scale here, I'll weigh it. Not sure if you'll be able to see the numbers, but I can see the numbers. Okay, so I'll read them out to you. So I've got 6 cups. I'm going to find the lightest one, the one with the least amount of water in it, and then I will put that one at the beginning of the list because I'm sorting it from lightest to heaviest. Okay, so let's try that out. Let's test out my my algorithm and see how many iterations or I guess times it takes, how many tests it takes, and there we can see the complexity. So this one, I'll weigh it, 14. Okay. And I'm going to grab some paper. Oops. And I will write down. Here, I've got some paper, and I'm going to write down on our first run, or in our first sort of test, 14. Okay, so this is our cup with 14 on it. This one, 107 grams. So we had 14, 107. So right now, this is my lightest cup so far, 41 grams. Let's try this one. We have 26 grams, 93. This is still my lightest so far. And this one, our last one, 123. Okay, so this is my lightest cup. I will put this one at the beginning of my list here, and then I will sort the rest of this list here, the rest of this 5. Okay. Next up. And the reason I can't say, oh, okay, now I have each of these cups, right? I'll just put them in order, is because this is an algorithm, right? So it has to work for any number of elements, right? So this one is 40 grams, 108, 91, 26. So this one has now become my lightest cup. And finally, 123. So this cup 26 gets put into my list here. And then I'll do the rest of these. You kind of get the picture now. Okay, this is my lightest one because I've checked all of them at 43. And then now I'm left with 3 cups, 108, 93, and that was 120, I think. Yeah, 123. So here we go. Boom. And then I'll test these 2. I'll find out this one's the lightest, and then this one. And now I've got my electronic waste sorted in ascending order. Okay. Does anybody want to try to come up with an algorithm that I could test out and see if it is more efficient than the one I just tested? Because this one took 1, 2, 3, 4, 5, 6 sorts at first. So it took 6, and then it took 1, 2, 3, 4, 5. So 6 plus 5 times I had to check. Right? So to find out that this cup was the lightest, I had to check all of these cups, right? And there's 6 cups, so I checked 6 items. This one, I had to check 5 items because there are only 5 unsorted cups. So 6 plus 5. This one, I had to check 1, 2, 3, 4 times. So 6 plus 5 plus 4 plus 3 plus 2. And then I don't think I had to sort with this last one. So we had 11 plus 4 plus 3 plus 2. We had 15 plus 3 plus 2. And then we have 2 plus 2. We have 20. So we had 20 sorts I had to do just to sort out 6 cups. It's kind of a lot, right? Did anybody want to try to take a stab and see if they could come up with an algorithm that would sort this thing better? If not, we can go back and we can look at some other algorithms and try to test them. Okay. So let's say I had a random sort of list. We can go on to the next slide, Ayush. Let's say I had a random list of electronic waste. Let's look back at our other algorithms and maybe think which one would be the most efficient for this sort of design challenge, and how would we apply the sorting algorithm. So somebody take a guess, and we'll try to see which ones. I'd like everyone to make a guess, actually. There's not that many people, so we can test all of them. So I want everybody to make a guess and try to test an algorithm and see how many iterations it's going to take you. So Nishtika, would you like to make a guess? Colina, Krishna, Caleb. And if you want to try this on your own, highly encourage it. If not, we can test it out on my end and I'll write it down. So maybe let's look back at our other algorithms, Ayush, just to give them a refresher. So there was bubble sort, and there was selection sort. There was quick sort, if you remember quick sort, insert sort or insertion sort, and merge sort. So those were the ones that we looked at. And then let's go to the list, Ayush. Let's go to the, sorry, not the list, the algorithm efficiency page. Yeah, that one. And maybe I'll spoil it a little bit here, right? If you want to take a look. Anybody want to pick one of these and I'll try it out on my end? If you are not. Okay, bubble, says Nishtika. Let's try bubble sort. Okay. So I think I remember bubble sort, but let's go back to the bubble sort just so I can remind myself. Okay. So go through the set or list again, swapping values or objects that are in the wrong order. Set is sorted when no more swaps can occur. Okay. So let's randomize my list. Let's not spill water on my laptop. I've been doing a lot of experiments with water recently and getting lucky. Or spill it on my notebook. I like this notebook. Okay. So because I was talking while I was sorting it, or while I was randomizing, I have no clue what the order is. So we should be good. So let's go through the list and swap values that need to be swapped and see how many sort of checks it's going to take. Okay, so let's do our first one on the list. Oh, got it. My scale turned off. Okay. We measure in at 108 grams, and this one measures in at 29 grams. Okay, so we have done one sort of check. We did one. So let us swap these. Boom. And now let's check this one and this one. 108, 123. So we've done another one. Now we're at 2. And because 123 is higher than 108, swap. Let's check this one. 108. Oh, whoops. I was not supposed to swap those. I was not supposed to swap those. This is what I mean when I'm talking. I can't can't focus. Okay. 124. 40. So we'll swap these. Now let's do I go back or do I just continue? I think I just continue, right?
Yeah, just continue. So yeah, once you have like the largest number and then you go back to the start again and do everything again.
So 123 and then 17 or sorry, 15. Swap. And then 125, 94. Okay, so that took us how many comparisons? That took us 1, 2, 3, 4, 5 comparisons. So that took us 5 comparisons, but we're not done just yet. We'll compare these two, this one, that's one comparison. They're in the right order. Let's compare this one and this one. That's another comparison. These are in the wrong order. So we'll swap them. So now we're at 2. And now this one and this one, they are in the wrong order. Swap. And now we are at 3. And now this one and this one is our last comparison. They are in the wrong order. So I will swap them and we are at 4. And the reason we don't need to check these last two is because we know this is the largest one on the list, right? Because we're kind of taking the largest one and shifting it down. So now this is the largest one. This is the second largest one because we've checked all of them and put the largest one at the end. So now we need to compare these 4. So this one, 28, this one, 40, no swaps, but that's a comparison. So this one, and then this one, no swaps. We are good. So we have done 1, 2, 3 comparisons. So now we will check this one, no comparisons. This one, we need to swap them. And we know this one is in the right place. So that is 2 comparisons only. And then we have just these 2 left to sort, I believe. This one is 28. This one is 16, and we will swap them. And that was just 1 comparison. So we have 6, 11. So we had 5 plus 3 plus 2 plus 1, which is 11 sort of comparisons compared to the 20. So that was pretty good, Nishika. We got it to be more efficient than our last algorithm. So let's go back to the algorithm efficiencies chart, and let's take a look at something where maybe it's already nearly sorted, right? So the reason that was better was just because the algorithm was designed a little bit better. But maybe in different scenarios, some algorithms might be better than others, right? So merge sort, remember Ayush said, is one of the best sorting algorithms, right? But in a scenario where, let's say, maybe your boss or your the person who was giving you the data said, this data, we're fairly certain it's sorted, right? But we need you to check, right? And make sure that this data is correctly in order. And they're going to give you maybe like 1,000 different sets of numbers or 1,000 different like sets of electronic waste. And then you want to sort it and then make sure that it is all in the correct order. So yeah, you could go with merge sort and it would be the best. It would do maybe not the best, it would do really well in most scenarios. But in a scenario where everything, you're pretty sure everything is almost already sorted, right? Maybe we can do something that doesn't sort of check every single number in a list that it's almost already sorted. So let's look at this algorithm efficiencies kind of table that we have here. And which one of these is completing the fastest in a set that is nearly sorted? So selection constantly performs the worst. Poor selection sort. It's just not that good, having to check the list every single time. Something like quick sort, which we looked at, does really well, maybe not the best. Insertion is what we are coming to a conclusion on. Yeah, I'm pretty sure you're right. I think I was just looking at it, and I'm pretty sure it's insertion sort. And yeah, okay, it does perform it does perform the best out of all of these ones. So maybe let's take a look at why. Let's just look one more time, make sure insertion runs better than bubble sort. Yeah, it does. Okay, but maybe that was just in the given set, so we can't necessarily draw a conclusion just based off that. But in this sort of example, insertion does run the fastest. So let's take a look at why that is. Ayush, let's take a look at insertion sort. Does anybody want to make a guess before we go to insertion sort about why insertion sort is the best? If you remember what insertion sort is. Something about putting it in the correct place immediately, I think if I remember insertion sort. Okay, that's fine. We'll give it like, that's fine. Let's go to the insertion sort page. Sorry, I keep making you switch pages. All good. So insertion sort, we remove each object from an unsorted group and set and insert it in its correct position in a growing ordered list. Does anybody want to tell me why insertion sort is performing as well as it is in a list that is almost already sorted? So we know what insertion sort does. We have a little graphic about it. No guesses? Remember, the chat isn't recorded, so if your answer is wrong, nobody will know. And your answer most likely won't be wrong. So the thing with insertion sort is that we're inserting it in the correct position in a growing ordered list, right? But our list is almost already ordered, right? So if we've got, I'll put my camera back here. If we've got this list, and this is totally sorted from our bubble sort of test, if we are to just switch this one or let's switch this one and this one, okay? So we'll remove each object from an unsorted group set and insert it into its correct position in a growing ordered list. Okay, so this is 20. This was a little bit higher. And then, so this is in the correct order. This is in the correct order. This is not in the correct order. So our set up to here is sorted, right? So now let's increase, right, the set that we're looking at up to here, right? And then we will sort this, okay? So this and this are fine. This and this are fine. This and this are not fine. So let's take this and let's put it in its correct order here. Okay, now this list is sorted. Now we'll check this. We are all good. And then we will check it up to here and we're all good, right? And because our list is almost already sorted, was almost already sorted, it only took like one swap to get it in the correct place. But something like merge sort, right, where we have to sort of split the list and split the list and then split the list again, right, is really good when we have an unsorted list or we have a random list. But when we know kind of what we're dealing with, I have to sort of move my camera. That way I can sort of show merge sort a little bit better. And maybe it's better if I angle my cups like this so that it's kind of facing. Yeah, I think that looks better. So now let's try our merge sort. So let's take us to the merge sort page, but I think I got it. I think I remember merge sort pretty well. So we've got our sort of total list here, and I accidentally split it down the middle preemptively. Let's divide our set into two. Okay, so now we've got one set, two sets, and then we will divide our set again into another set. So we'll take this as one set and this as another set, and then we'll divide this set. And then now we've got our sets, and then we'll divide this set and then this set, okay? And now when we merge them together, we are going to sort as we merge. So let's merge this one together, right? So we make our comparison, we're good, okay? Remember, we're still dealing with our nearly sorted list. Let me do it this way, actually, where I had this one and this one, same way that we did our insertion sort. Okay, so now make our comparison, bring them together, all good. Now we bring these ones together, make our comparison, put them into a set, make our comparisons, all good. We'll bring these ones together, make our comparisons, right? Remember this one and this one are still in the correct order relative to each other. And then we will add this one to that set, make our comparisons, we're good. And then when we merge these larger sets together, make our comparisons, and they are not good, but these ones get swapped, right? And now we see, right, how many comparisons we made doing merge sort versus how many comparisons we made during insertion sort, right? So we had to compare, and then we brought them in and we compared. So that was 3. And then we compared, and then we compared, and then we brought them in here, and then we compared. So actually, I think that was 1, 2, 1, 2. So 2, 2, and they're separate. And then when we brought them together, 2 plus 2, and then we compared, and then it was 1. And then that was like 5 comparisons. So merge sort, still really efficient. Not as efficient in some scenarios as insertion sort. So now you're thinking, maybe what should we do? Is there ever a scenario where insertion sort is worse than average? Yes. If our set is almost reversed, you see how it has to kind of compare everything over and over and over again, because it's literally in the worst way possible. It's in the worst form possible for insertion sort, right? It kind of has to compare every single thing, and it's almost dead last, just falling behind selection sort, which is always going to be last, and bubble sort, which does not perform well when the list is reversed either. Okay, so let's take a look at our solutions. We made our models. Ayush, let's take us to the slide after design a solution. So we did our sort of filling of our containers, and we we don't really know which one of them is which, because my water is clear. But if you were to use sand or coins or something, cover the top, and then mix the order of containers so you don't know their weights. We did that, and then we applied our sorting algorithm. So if any of us have our cups or our coins or sand out, go ahead and test it out. And let's just let's give it like a couple minutes if you wanted to try, and if you wanted to try this on your own. Okay, so I'll let you guys try it out for a couple minutes. And maybe we can go back to, I think maybe bubble sort, because that was a pretty interesting one, Ayush, if we want to take them to bubble sort. Let you guys try it out quickly. Or you can work along with me, and I will do it on my own as well. So I'm going to take out just 1 cup just to eliminate some unnecessary moves. Go through the setter list, swapping values or objects that are in the wrong order. So I'm going to go through my set, swapping values or objects that are in the wrong order. Comparison. These 2 are in the right order. These 2 are in the wrong order. Okay, so now we have our largest one at the end. This one is 40. This one is 16, 15. Swap. Swap from 40 to 25. 40. We are in the correct order. We don't need to compare this one. 14, 27, 27, 41, all good. And then we are good, as we don't need to make any more swaps. Okay, let's go to our test and evaluate slide. I think that was about 3 minutes. That took us about 3-4 minutes. So how long and how many steps did it take to sort the groups of unknown weights? So does anybody remember using bubble sort, how many sorts it took for me to try? Or if you tried it on your own, let me know which sorting algorithm you used and how many steps it took. Or if you are trying it, let me know, and we can work through that. So we'll use our bubble sort as an example. It took us 11 steps to sort the groups of unknown weights. It took 11, I think, comparisons. So did it work? What should we change? So did it work? Yeah, our algorithm did work, right? Or my initial algorithm where we did 20 comparisons did work. But I think it was kind of similar to insertion sort. So what could we change? Does anybody have any changes they could make to the algorithm I came up at first, where you take the first item and then you count the weights of every single other item and then swap it? Or bubble sort? Or did anybody learn anything about algorithms? Because one interesting thing, I think, kind of when we talk about what order does our list come in, or what kind of order does our list come in the beginning, right? Do we know that it's almost sorted? It's almost sorted in a reverse order and stuff like that. So if you were to make an algorithm, right, what kind of changes that you learned could you apply to it? Ayush, do you want to give us an answer? If you were to come up with an algorithm, right, what would be the first question that you would ask, maybe, to, or what would be the first thing that you would do?
Think how randomized it is. Maybe I'll ask if it's nearly sorted or if it's reverse order, because we know all like the algorithms work differently in like different scenarios.
Yeah, exactly. That's a really good first sort of question to ask, is how is my data coming in? We have an answer from Nishtika. When you pick a sorting algorithm, is the algorithm, oh, this might be a question. When you pick a sorting, I just dropped my pen cap in the water. Is the algorithm chosen used for all sorting situations, nearly sorted, unsorting, or can you choose different sorting algorithms to use in a certain situation? So when you pick a sorting algorithm, let's say it's an example where you're working and let's say somebody gives you a a list of you get a bunch of lists of numbers, right? From like 1 to 10, and then you have like 100 of them, right? You have 100 lists, and each of those lists contains a number from 1 to 10 and in a randomized order. Let's say you know that it's coming in a randomized order, or if you don't know, you can kind of just assume it's coming in a randomized order, right? What you would want to do, or what you would have to do, is you would have to pick one sort of sorting algorithm to use for all of those lists, right? But if they were to say, okay, the first 5 of these lists are almost all sorted, and the second half of them, the next 5, are not sorted at all, right? So the first 5 are kind of sorted, the second 5 not sorted at all. Yeah, you could use 2 different algorithms, right, to sort of match those 2 different situations. But if you don't know, the best thing to do is assume it's random. So yeah, okay, no problem. Yeah. Research and identify as our challenge. So our challenge for today is try to research and identify other sorting algorithms. Can they produce more efficient results? So we looked at merge sort, we looked at quick sort, bubble sort, insertion sort. I feel like I'm missing one. But if you can find a new one that we haven't talked about today and would like to share it next class or next sort of session, be very happy to hear it. And we are pretty much done for today. If you have any questions, be very happy to answer them. But besides that, we can dismiss. So feel free to, we are going to stop the live stream right now. Ayush, if you would confirm that it is, or let me know once it's stopped. And if you have any questions,